what I want to do instead is to introduce the idea of a network on chip. Like I said, we will not be diving deep enough to sort of understand what NOCs, how they are implemented. We are going to look at a lot of the terminology so that you can at least understand the core ideas of NOCs, why they are useful, and what are the different considerations when you are actually trying to implement NOCs. Okay? So this figure out here, you don't need to worry about the details. It's there for just one reason, to show that a modern SOC is complex. Okay? Look at the number of modules that you have over here. This is the actual CPU, right, sitting in one corner. It has its own instruction cache, data cache, etc., right, which are just literally attached directly to the processor, right, they don't even come on the bus. Then it, and in fact it could have multiple CPUs out here, right. All of these are AHB bus masters who are talking to the AHB multilayer bus. AHB is the AMBA high performance bus, right, AMBA being the advanced microcontroller bus architecture, the original 2.0 version of the ARM bus, right. So you will notice that for most diagrams or documentation or anything that is describing the AMBA or AXI buses, it will be based on ARM processors. But like I said, nowadays, especially with AXI, not so much with AMBA, but with AXI, the newest version of the bus, it has been very widely adopted by a number of other kinds of processors as well, right. So it's very likely that you can come across, for example, a RISC-V based system with an AXI bus interface. But this ARM processor has access to an AHB multilayer bus. Look at the number of peripherals it has to deal with, right. There is a DMA out here, there is an LCD for display, then there are a large number of these BIUs, are basically bus interface units. It's talking to a memory controller which has to deal with a whole lot of different types of memory, flash, DRAM, SRAM, DDR memory, right, all of those. There is a USB peripheral, there is an Ethernet peripheral, there is some ROM which contains static configuration data, right. There are some other instruction memory, data memory, a CAN bus which is used for, it's basically a controller area network, right, it's used for certain kinds of control applications. And then you have the bridge, the AHB to APB bridge, on the right side of which you actually have the slower peripherals, right. The slower peripherals include a watchdog timer, boot control, some interrupt control unit, timers, real-time clock, right. You already have something like this. One system on chip has something like one processor plus around 25 or so peripherals, right, not 25, I mean close to 20 peripherals, okay. And this is a relatively very simple SOC, okay. So how does this get complicated? What happens is, typically in a modern SOC you would have multiple of these things. You would have multiple network interfaces, you would have GPU accelerators, you would have graphics accelerators, you would have accelerators that deal only with sound processing, there would be some other accelerator for doing the baseband processing for modem communication, right. By the time you add all of those together, there would be other things for error correcting codes, right. You add all of those together and the number of such peripherals that are talking on the bus nowadays can easily hit 20, 30, 40, 50, right, and the number is expected to keep increasing, right, because you can already see that one of the things that happened in the past 10, 15 years is that if you had noticed, if you have gone back and read the history of how processor development went along, throughout the 90s and into the mid 2000s, the entire nature of the game was just clock speed, right. So in 1995, for example, having a 100 megahertz processor was a big deal. Somewhere along the line, by 2000 they had hit 1 gigahertz, right, but then it started slowly saturating. They went up to 2, 3, reached 4. At that point they essentially found that the power bottleneck was such that you simply can't go to higher frequencies, okay. So then instead what they said is, let's play the parallelism game. We have these transistors, we know how to integrate more and more transistors, we don't know what to do with them, right. we are not able to make them run any faster, so let us use them in parallel, which is where the sort of multi-core game started, right? Dual core, 4 core, 6 core. So laptops now have 8 core processors, for example, right? Are they really using them? Probably not. Then of course came the GPU, hundreds of cores, thousands of cores, okay? So the point is, in principle you can start thinking of any of these things as potentially peripherals that are all talking to a single bus, right? Even if I have a many core system, then I can actually think of it as having, you know, hundreds of bus masters talking on the same bus, okay? Obviously, if I try having one bus as the bottleneck between all of them, that becomes a major problem. I can't afford that. But more importantly, the question is, how do I even build such a system, okay? So that essentially led to the question of, should I even, and you know, a related problem was, what happens in the synthesis flow itself, right? So over here what we have is, we start with an architectural specification, which is a high level block diagram like the one that we saw here, right? So this is an architectural specification. It's telling you what the blocks are and how they are connected to each other, logically connected. If I take that same architectural specification, right, and go through to physical implementation, what usually ends up happening is this figure that you see on the bottom left, right? For those of you who might have gone through a complete process of actually taking a chip through the synthesis and then place and route, you will see that this is not unrealistic. It may not be this bad, this is obviously an exaggeration of how bad it is, but you would definitely end up with something of this sort, right? In particular, you would have one block which all the red units, for example, you know, this would all be one block of red, this would be some other red which would spread around over here, this red would also spread around over here. Even if you do sort of detailed floor planning, placement and so on, you will soon find that it starts becoming messy, right? The yellow will have to sort of spill around somewhere here, they will overlap, then there will be some green which starts off over here but then goes into this, right? It becomes very messy very quickly, right? That's essentially what this will look like. That's at the placement stage, and once you do the routing, you will end up with wires going all over the place, and the net result will finally be something like what we are seeing on the bottom left, okay? Why does this happen? Because the synthesis tools are essentially taking these large number of gates that you have and trying to optimize them. They are trying to optimize the placement, they are trying to optimize the routing, they want to minimize the wasted area as well as the length of the wires, okay? So they say, look, anyway you are not going to go in there and actually try and fiddle around with these gates, let the tool actually just decide the optimum placement so that your performance is best. This is what you end up with. It's not just that it looks bad, the bigger problem is the synthesis and place and route for a tool like this, right, can take days, literally days, not minutes or hours, days, right? So IBM, when they talk about their power processor design, for example, one part of their processor, when they do the place and route, every run for that literally takes about a day or so, and that's just one part. There are probably around 20 such parts that they need to put together, okay? And these are on machines that have a terabyte of RAM, okay? So this is clearly sort of got to the point where it's running out of control. The proposal, which was basically made by William Daly, originally in DAC 2001, and since then he's been promoting it. By the way, William Daly was a professor at Stanford, I think still is, but is also the chief technologist at NVIDIA, okay? So he proposed this idea that, look, change the way that you look at the architecture specification itself. Let's modify it slightly so that rather than just having this bus and all the things connected to the bus, let's think of these tiny blocks over here as just being network switches or routers, right? So effectively every one of those blocks now has the ability of taking a packet of data and deciding which way it needs to go, The simple way of thinking about it is north, south, east or west, right? Directions are sort of specified that way usually. So each of those routers can take incoming data and switch it to some other side. Okay? What that means is each of these blocks, now in principle there is no reason why the blocks even need to be sort of specifically, even from the architectural diagram point of view, right? I can change their locations, because after all that I care about is the block by itself does some work and then needs to send data to another block, right? So if I think about it that way, that I am no longer worried about directly accessing memory or copying an array from here to there. If I think in terms of packets that need to be routed, right, I can simplify my diagram, my architecture diagram, so that it now looks more like a logical network, right? His way of putting it was route packets, not wires. Don't do the wire routing that you have over here, do the packet routing instead. That comes about with this diagram. The interesting thing is, if you really go with this approach, then what ends up happening is that your final placed and routed physical implementation looks almost identical to your architecture design. Why? Because you can literally place it exactly in that form factor that you had originally designed with and just put a network interface next to it. Okay? So you need to create these physical routers that are capable of taking packets and sending them somewhere else. Okay? Now, how does this work? On paper it's very nice, very elegant solution. In practice, of course, it's a lot more complicated than that, because two things have to change. One is the way that you look at the problem has to change. You are no longer thinking in terms of blocks of data, that is arrays and some computation that just runs for loops and so on. You need to be able to think in terms of packets that need to be moved around. Okay, so that changes the way you look at how you implement, right? And the second thing is, what exactly do these routers look like? It's easy to just say put a router, right? But is that itself going to be very complicated and hard to implement? We don't know yet. Okay. A related thing, which is also part of the motivation for this, is simply this observation. Wiring delay essentially grows quadratically, right? Why? Because as we move to smaller technologies, the current delivery capabilities are first of all decreasing, but more importantly the capacitance, right, because the vertical height sort of remains the same, the thickness reduces, right? If you do the calculation, you will find essentially that you can show that for a given length of wire, the delay will grow quadratically as you go to smaller technologies, or rather the other way. For a given technology, as you increase the length of the wire, the delay through it does not grow linearly with the length of the wire, it grows quadratically. Okay? What is usually done is you insert buffers. Okay? Those of you who have done digital IC design, you will know that there is this optimal buffering that can be placed, right, which allows you to reduce the overall delay through a chain of, or through a long wire. Okay? But that's not easy to do either, and those buffers themselves are expensive. So the observation essentially went, if I have to do buffers in any case, right, maybe I can just insert a cycle break, one cycle, do pipelining, and say I am going to delay a signal by 1 clock cycle before it reaches its destination, right? And if I am doing that, why even bother with buffers? Why not just think of them as routers, right? You just send the data to the nearest router, and I then only need to optimize links from one router to another. I don't need to worry about directly taking a wire from one place to another. Okay? Okay. There's one small useful piece of information which is there in Dali's presentation. Okay, I'll forward that later at some point, which basically gives you a stronger motivation for why we are doing this. Essentially, the observation which was made quite a while back was even about 20 years ago, the energy required to transfer the energy and the delay involved in transferring a 32-bit value across a 10 mm chip, right, a 10 millimeter long wire on a chip, right. Already at that point in 2001, the energy required for transferring that, or the delay required for transferring that, was twice the delay required for a 32-bit arithmetic operation, in other words adding two numbers together. Okay. By 2010, that factor had become almost 10:1. Okay. Because what ended up happening is, as transistors get smaller, the delay through them becomes less, which means that the arithmetic delays start dropping. On the other hand, the current delivering capabilities of the transistors also decrease, which means that their ability to drive a signal across 10 mm has decreased, and it ends up taking longer. Okay. Now, why 10 mm? Because that's more or less the size at which a chip is considered relatively, fabricatable without having very bad yield. Okay. There are chips larger than that, and there are many chips that are much smaller than that. So 10 is not a very small chip, right? But for the kinds of SOCs and large processor systems that we are talking about, 10 mm is probably a reasonable length for a wire to travel. Okay. So all of this finally led to this motivation for the network on chip. What we are going to do is, rather than looking at specific implementations, we want to understand some of their characteristics, right? There are many defining things over there. The topology, or in other words, how they are laid out or how they are constructed, how they are connected together, is one of the most important ones. This is what we will look at in a little bit detail, right? Other things such as the routing algorithm, switching strategy, flow control, and so on, we are not going to look into that at all in this course, right? For those of you who are interested, Professor Madhumutyam in computer science has been working on networks on chip for quite a while. So his students have in fact worked on various aspects of the routing and switching strategies over there, right? But we will not be looking at those in this course at all. The other thing that we really need to understand, apart from different kinds of topologies, is specific metrics that are used in order to understand how good or how poor a particular topology is. Okay. So this is what I mean by topology. These are examples, right? This first one is something called a 2D mesh. The name is sort of self-explanatory, right? Essentially what it says is, it's a mesh architecture. You have all these nodes that are processing elements, and these are the links between them. Okay. So the assumption over here is that the processing element also has the routing capabilities, or alternatively you can think of it as just a router alone, right? In which case I would then have a processing element sitting connected to it, right? Either one of these views is perfectly fine. Either I can think of those circles as the routers that are just moving the data around and the processing elements are sitting next to them, or I can say it's the processing element but also has routing capabilities within it. Okay. So the mesh is very easy to understand, right? It's sort of an obvious way of connecting things given that you have a planar structure. The problem with it obviously is, what happens if this one wants to communicate with this one, right? It has to jump through an intermediate stage. That brings us to the idea of a torus, right? In the torus you do precisely that, you make these connections from one end to the other. Okay. It shortens the distance from between the endpoints, and in fact potentially also gives you two ways of reaching the same place. Either I can go clockwise or anti-clockwise in order to get from A to B. So supposing I want to go from A to B, I could either choose to do it directly like this, or I could go like this. Both of them are valid, right? Presumably I will only go using the shorter path, but there can be situations where the shorter path is blocked for some other reason, and therefore I need to use the longer approach. Okay. So the torus sort of takes the idea of a linear set of connections and just folds it upon itself, right? The hypercube is another sort of layout similar, right, which basically says that now I have connections in 3 dimensions, okay. Now obviously the torus and hypercube are not really friendly for layout. There is a problem there, right? I mean, it's all very fine to say that I will just connect this end to that end, but that means that I have long wires, which is what I was trying to avoid in the first place, right? But it's a trade-off between, is this worthwhile from the point of view of the actual implementation, and what kind of benefits do I get versus what kind of penalty do I have to pay for these long wires. Going further, there are a few more sort of broad topological structures. The ring is essentially saying that I'll take all 0 up to 7 laid out in a straight line and just connect them into a ring instead, right? The octagon in this case, supposing you have 8 processors, has a ring plus in addition cross connections, okay. Why is it brought in? For a simple reason. Supposing I wanted to go from 0 to 4, that's the worst case connection inside a ring, right? Whereas over here I have a short direct connection. What that also means is, supposing I want to go from 0 to 5, this is usually 3 steps, 3 links or hops, right? Whereas over here it now becomes 2 hops, okay. So having those direct short connections, short circuits across the system can help. Incidentally, one thing that has sort of driven a lot of this design process is this idea of so-called small world networks. Okay. So there is a game that started somewhere in the US obviously, called 6 Degrees of Kevin Bacon. Have you heard of that? Okay, you might have come across some variant of that game, right? Essentially the original game 6 Degrees of Kevin Bacon said you pick a random actor or actress, right, and can you connect them to Kevin Bacon within 6 steps. What is a connection? You can basically say that this actor essentially acted in some other movie with XYZ, XYZ then acted with ABC, and ABC directed a movie that Kevin Bacon acted in. Okay, so that's 3 steps. Okay, and essentially it's interesting. You look at it, the large number of actors and actresses that are there in Hollywood. In spite of that, you can pretty much find a less than 6 degree connection to almost anyone, right? There is another thing in maths called the Erdős number, which you might have heard of, right? How closely are you connected to Paul Erdős, who is one of the most prolific mathematical publishers and mathematicians in terms of publishing of all time, right? The point of these small world networks is, even though you have a very large number of points that need to be connected, there are some long range links, okay, which suddenly end up making 2 different parts of this set of points that you want to connect come close together, okay. That's the kind of thing that you are trying to solve in the network on chip. You are not necessarily interested in finding a very regular structure, or ideally you would like a regular structure, but you are thinking of ways by which I can quickly get to my destination. So if there are a few long range links, right, they might allow me to sort of make use of them if I actually want to go across large distances in a shorter number of hops, right. Obviously there is a price to be paid for those long range links, which is that they are long, they are going to be expensive, they are probably going to consume a lot of power as well as delay, right. But if you have relatively few of them rather than having a large number of them, it probably is worth it. So the small world networks are, that idea comes up a lot in the design of networks on chip, okay. The crossbar is the opposite extreme. It's the smallest possible world. Everybody is directly connected to everyone else, right. But as you can see, the problem with the crossbar is precisely that. Everybody is directly connected to everybody else, just too many links. Routing a crossbar can be a nightmare.